chapter 13. Let's see what's motors. It says objectives: explain the basic components of a motor, list various classes of motors, calculate motor starting current. Use a code to design motor branch circuits, include overcurrent protection, define and compute true power and apparent power, and the power factor. Convert electrical energy into mechanical energy. So what does a motor do? A motor, look here. Motors are found in nearly every industry, ranging in motor size and from a fraction horsepower to 1,000 horsepower. Electricians, design, and engineers must have a firm knowledge of motor types, circuit requirements to properly install and maintain motors. This chapter will briefly explore some of the basic various motors and basic motor installation. Article 430 of the code covers motors. Okay, so motors, good now into motors. So motors, they get the electricity and use electricity to give you energy, mechanical energy. Okay, so they use electrical energy to give you mechanical energy. They do work for you. So we apply electricity to them, it does work for us. The generator, in reverse, now we provide a source to turn it, and then it gives us energy out of it. So the two different basics, so you understand, a motor is going to do work, and a generator is going to give you so you can do work. It's giving you the mechanical. So you have to add a mechanical to turn the motor to give you electrical energy. When you apply electrical energy to it, it turns around and does mechanical work. The two principal components of a motor are the stator and the rotor. The stator consists of one or more windings, coils, and wire and surrounding the rotor. And the windings in the stator, sometimes called windings or field coils. And then the rotor is a cylindrical component housed within the stator. Both ends of the rod extend through the motor, are set for bearings allowing the assembly to turn. These are the two types of motor: squirrel cage and a wound. A squirrel cage motor houses a ring of copper or aluminum bars parallel to the rotor axis, and the wound rotor has a coil called armature coils connected to the commutator. Segments of the commutator receive currents and brushes into use in very different types. So let me go back a little bit here. So here we have, here's our rotor, and here's our field windings. Okay, so if we can provide an energy, and then it makes the magnetic field, and it's alternating, there's alternating, so that's what makes the motor spin. Okay, the other is they apply it to the end to help the motor turn. So the induction motor has a primary winding connected to the power supply. There's motor types. This is, let me get, before I get, I'm getting ahead of myself. It says motor differ in various ways. The current supplied to the motor can be a single phase or a polyphase, AC or DC. There are different ways to starting the motor, different ways to keep the motor running, internal mechanisms, everything. So again, some of them you apply a DC circuit to the commutator that would be up in front that helps allow this to turn, the motor to turn. Okay, so if you ever hear anybody talk about a knuckle where you make your connections, they call it a knuckle because you usually bust your knuckles trying to get these wires back inside, especially when you got them 100 horsepower motors and stuff. So this is where your connections would be. That would be called the knuckle. The slang for it is knuckle instead of connection box or J box or whatever you want to call it. There are two classified AC motors, the single phase and a polyphase. Single phase motors are used in residential light commercial applications where the service is single phase volts. The most common type is a polyphase motor, are used in three-phase currents. The three-phase motors are more efficient and can use the larger loads with single-phase motors. So always remember is when you have a single-phase motor, the difference between a single-phase and a three-phase. Okay, when you have a single-phase, if it's say 120 volts, okay, whatever's on the hot, that's it. It's going to take. Let me get mine. So I got a 1 horsepower motor. And that would be 16 amps at 120 volts. Okay, I get the same 1 horsepower motor, and I apply 3 phases, let's say 208. Okay, so 1 horsepower at 208 3 phase, 4.6 amps at 208 volt 3 phase. Okay, so this was 430 248, and this is 430 250. The code's where I got them from. So you can see the difference. At a 1 horsepower motor at 120 volts, or it's 16 amps, and then at 208 3 phase is 4.6. If you go to the same table and you take it to 230 volts, this is going to be half. Yeah, so if I got a single phase, a house, or light commercial, getting this motor here at 1 horsepower at 240 volts, okay, 430 248, that same motor would be 8 amps. Is half the amps of the 120. Okay, anytime, again, you get that to 208, if it's single phase, and then you got to go back, if the motor itself is a single phase, even though our power is 3 phase, and it's here, we have to go back to this table even though my applied voltage to a motor, if it's single phase, still 208, but single phase. Because all I got two hots coming to it. I don't have 3 hots coming to it. I have 2 hots. Okay, it's 208 volts, single phase. That means I got 2 hots coming to it. Okay, you may have a 3-phase system, but you may not have a motor that is 3-phase just because it says 208. So I always have to remember, look at the nameplate. Okay, when you're doing a question, hopefully they will explain that it's either single phase or 3-phase. Okay, if you're doing something and they do not mention, if you got a 208 volt and they don't mention single phase, then it's automatically 3-phase. You know, if it's 120 volts, that's single phase. You know, that's 1 hot. So you would go to 430 248. If it was a 3-phase motor, then you would go to 430 250. Okay, here I have a single phase motor. I said it's a single phase motor because I labeled it single phase at 208. So I would go to 430 248 because my voltage is not 3-phase. What's the difference? It's at 1.732. Guess what? The amperage is still the same. The amperage is still the same at 120 volts. So if I get that 120, So what it is my current is divided into 3 hots. Why is it here 16? Why is it here 4.6? Okay, the resistance, you just can't say, oh, okay, let me divide 16 by 3. No, because of the resistance has changed. That's why ampacity's changed. Except when you have the 120 volt or 240 volt. All you're doing is cutting the resistance in half. Okay? Or you're adding the resistance in half. I'm sorry, adding the resistance in half. So my resistance, let's say here my resistance is at 120 divided by 16 equals 7.5. Okay, all I did was R equals E divided by I. So 120 divided by 16, R equals 7.5. Okay, so I can't, that's not the physical resistance. I just can't say, well, I'm just going to multiply I equals E divided by R. So I just can't do that, because if my voltage doubles and I keep the same resistance, well, guess what's going to happen to my average? My amperage is going to double. Because if I do it that way, so obviously my resistance is doubled. For it to drop half, my resistance went up. So always remember is resistance and voltage are directly, resistance and amperage are inversely proportional. If one goes up, the other goes down. If the one goes down, so if my resistance goes up, my amperage goes down. So more like here, my resistance doubled. Curious. So let's say I have 240 and my resistance went up to 15. Doing this live. So 240 divided by 15. Oops, I'm sorry, my resistance quadrupled 4 times. Okay, so there is what I did. If my resistance goes up, my amperage goes up double, so it stays the same. Because I increased my resistance still stays 16 amps. So it's going to be quadrupled. If I go down half, yeah, it's quadrupled. So that would be 30 T40 divided by 30. Okay. So this went up 4 times. Okay. That's how resistance changed, because of the motor change. Motor changed. Alternating current. So we have on the single phase motors, we have a split phase motor and a shaded pole motor. This says an AC induction motor has a primary winding stator connected to the power supply. The secondary winding in the rotor carries the induced current. Unlike other motors, induction motors have no physical connection between the energy source and the rotor. And the current used by the rotor is derived from the electromagnetic induction from the stator windings illustrated in the induction motor. So again, these windings create that magnetic field that turn the rotor. So there's no physical connections between the two. That's your average motors that we use. And then we have a shaded pole. The shaded pole motor has an auxiliary coil, shading coil embedded in each field. Each coil forms a loop within the running windings. These cause the motors to have very low starting torque. So, where is it here? They didn't give me a motor on it. But you would have, if you see that video that I told you to go watch on AC/DC motors, creates this magnetic field. Okay. Single phase AC motors, capacitor motors. You have a capacitor motors, a capacitor start, a capacitor motor, a capacitor start motor, and then a permanent split capacitor. So a capacitor start motor is you have a capacitor that helps start the motor, and then once the motor starts, the switch opens up and it takes the capacitor out of it. It says a capacitor motor has an auxiliary windings connected in series with a capacitor. These motors have low starting torque but have high torque. A capacitor start motor. This type of single phase motor is identical to the split phase motor with a capacitor added to create a higher starting torque. The capacitor is connected in series with a start winding with a centrifugal switch. When the motor reaches its running speed, the switch opens and the capacitor and auxiliary windings are removed from the circuit. So that's this one here. And a permanent split motor is also called a capacitor start run. These motors have no switch, so the capacitor remains in the circuit while the motor is running. This type of motor has a high running torque and high starting torque. Repulsion motors operate using the principle of magnetic repulsion. Currents flow through the field windings of the stator, through the coils and the wound rotor. The interaction of the magnetic field produces the field, and the armature coil causes the motor to turn. Repulsion motors are sometimes called series motors because of the field and the armature windings are connected in series. The following are the three timing types. So we have a so here's the field stator, and then here's the brushes. So that would be like in the front. Let me see if I got a picture on here. No, they don't have the picture on here. But if you go to figure 13.5, that's where they have it. So you have a repulsion motor. This motor uses repulsion to start running. Repulsion motors have a higher starting torque. Repulsion induction motor, in addition to the repulsion motor windings, the motor also has a squirrel cage winding in the rotor. And a repulsion start induction motor, this motor is similar to the repulsion induction motor but has a set speed commutator. Bars are short circuited and the motor operates on induction alone. Three-phase AC motors. Three-phase induction motors do not require a commutator to change the polarity of the current. The varying alternating phases produce a magnetic field that drives the rotor. Synchronous motors have rotor poles that are energized by a DC generator called the exciter. These motors operate at constant speed and have a controllable power factor and can be adjusted by the motor operator. They are rarely smaller than 25 horsepower. Direct current. Three different types of motors: shunt wound, series wound, and compound wound. These motors differ in connection between the field and the armature windings. Shunt wound motors, these fields armatures are connected in parallel. Here they are, the shunt and the armature. Shunt wound, a series wound motor, or shunt wound motors, the one on top, and then series wound, your field and your armature are the same. In a compound, this motor is connected fields, windings, one connects in parallel and one connects in series. So you have a shunt field, a series field. They call it series because it's in series with the armature. Universal motors are usually small series wound motors that can operate on DC voltage or single phase AC voltage. The motor's performance is independent of the type of voltage. These motors are available in sizes up to 3/4 horsepower. Universal motors have an armature, brush field windings, and commutators. See, the field windings are connected, and you can see it down on 13.5. I wish I would have put it on here. So you're applying an external source to the armature in the front. So let me go back to the motor real quick. So your commutator and armature and everything would be out here, and this is where your power helps start this motor, exciter. The universal motors, this is DC single phase AC field windings connected in series with the armature and the brushes. Okay, so, and you're exciting, this is outside the motor. Motor torque. You look at my time here. This is force that produces rotation, lock rotor torque, or starting torque, pull-up torque, full load torque, and breakdown torque. So the motor torque is lock rotor code torque, also referred to as the starting torque. This is the torque produced by the motor when it initially starts. Is also the force required to get the motor running. Pull-up torque required to bring the motor to full speed after it has been started. Full load torque, the torque necessary to keep the motor running at rated speed. Breakdown torque, the maximum torque a motor can achieve before stalling. And then it's giving you torque calculations. It's got the formula up there. That 5252 is a constant. That 5252 is a constant. Okay, in the example it says determine the full load current developed by the 50 horsepower having a 240 volt supply turning at 1800 RPMs. I'm not going to use that, I'm just going to use something else. Because that one's there. Okay, I got a 3 horsepower. $230 volt or 60 volt, 3 phase, 7.8 and 3.9 FLA, and it has 1760 RPMs. Okay, and I'll give you all some, I'll look up some nameplates and I'll stick this up in a question and I'll send it out today. So our formula, T equals horsepower times 52 divided by the RPM. So my horsepower is 3 times 5252 divided by my RPM, that's 1760. T equals, let me get my calculator. So T times 5252 divided by 1760 equals 8.95. So, producing 9 pounds of torque. Okay, so it's producing 9 pounds of torque. So, very easy. So what is the torque to turn this motor? It's the formula. Again, that 5252 is a constant. So you can see I did it there. I just put in nameplates, and that's what I'm going to do right now. And then I'll put some questions in so you can do these formulas. And I'm going to drop it here, and then I'll get the next video going on the next page. Alright? It was good meeting yesterday. It was nice seeing you all's face too. It was nice seeing you all on that Zoom. So we'll continue doing that once a week at least. Make sure we're everybody up to par and everything. Alright, y'all have a good one. Enjoy the video.